scales, the spatial scales. Sorry, I have a pop-up here.
Sorry.
I don't. Sorry for that. So it's universal. So we have it, for example, in liquid crystals at a micrometric scale, also in chemical reactions at a millimetric scale, in granular systems, forming patterns, for example, in the dunes in the desert, and also what I'm most interested in the pattern formation in a living system. In particular, what I show here is a pattern formed by vegetation biomass. Here you can see every right here is a whole forest, so it's a really big pattern in nature. So what we do to try to understand all these complex systems, so we start with some observations, for example, the chemical reactions here. Then we try to model them based on, for example, physical principles, symmetric arguments, or whatever, and we create a dynamical system, okay, that tries to describe how these variables will evolve. And then one usually makes a numerical simulation or tries to solve the dynamical system analytically, and then one see if the description that one creates is good enough or if it's something missing. So now I want to try to explain what is the reciprocal and non-reciprocal coupling. So this property has to do with the mathematical structure of the dynamical system. So for every physicist, the most common system, I would say, is an array of masses coupled with a spring. And we all know that in this array of masses coupled with springs, one covers the wave equation. Okay. In particular, if one describes the dynamical system, if one writes the equation of motion based on Newton equation, for example, one has the acceleration, then a force, and then there is this important term that says how one mass is coupled with the other, okay? In this example, the coupling is linear, but you can also have nonlinear terms also. And this element, this matrix elements A sub I j will define the mathematical structure of the dynamical system, and in most of the usual physical configurations that one studies, this matrix happens to be symmetric. So when it is symmetric, it characterizes a reciprocal coupling, meaning that one mass affects the other in some way, and if you interchange them, the same happens. So there is no difference if you interchange these masses. Whenever this matrix is not symmetric, it means that the response will be different according to which mass perturbs the other. Okay. So whenever this matrix loses its symmetry, we will be speaking about a non-reciprocal dynamical system. So here are some small motivations for this. So non-reciprocal coupling is really intriguing because it serves as a way of direct the propagation of energy and other properties of systems, as you can see here in this small video, where some researchers created system with non-reciprocal coupling based on robots. So these robots are able to feel the neighbors and apply some force, and then the equation for these are characterized or described by a non-reciprocal coupling. So what happens is that you can see that for perturbation, the amplitude of the waves is only amplified in one direction compared to the case of our reciprocal coupling. This is what motivates us the most. And for instance, if you start to give more degrees of freedom, in this case, these are like self-probing particles, and you have two species with also having reciprocal coupling, you can start to create, for example, rotations without an external torque. So reciprocal coupling is able to create really fascinating dynamical behavior. Okay, so I will start with my first word, reciprocal Frankel-Controllable chain. So our objectives are to include non-reciprocal coupling in a general nonlinear dynamical system. Okay, and then try to analyze theoretically and numerically, and if we can, analytically also, the effect that it has on nonlinear waves. The video I showed you before, the system was linear, so now we want to extend this to nonlinear systems. So how we do this? We start, for instance, with pendulums, because pendulums are the basic nonlinear system that we all know. Okay, due to the restrictions of the motion of a pendulum, the wave is a nonlinear function that acts on it. Then we introduce a non-reciprocal torsion spring that, similar to what these robots do in the previous video that I showed you, it is able to feel if it is being perturbed from the right or from the left. Finally, one constructs the equation of motion, and one can see here in the structure that one has a non-reciprocal coupling because this matrix that I talked about to you is non-symmetric. Okay. I want to say also that this model, the Frankel-Controllable model, is not only like a toy model of pendulums, it also appears in other dynamical systems, physical configurations, like in magnetic wires, also in arrays of short lossy conjunctions, and also it was a very important model to understand the defects in crystals, okay? So it's rather an universal model that it tends to appear in several dynamical systems. So first, we analyze the overdamped limit of this equation for simplicity, okay? Later we plan to extend these results. So whenever this condition in the equation is false, we can simplify the equation to this one. That is the one that I will analyze the dynamics of. Okay, and we baptize this equation with the name of overdamped non-reciprocal Frankel-Controllable adaptation. Okay, so what we expect in this equation, first of all, we will be fixing the first pendulum of the chain to be in the position. Okay, the theta variable measures the angle with respect to the opposition, and what one expects in the normal situation is fronts into the unstable state in this configuration. That means that one expects that if one makes a perturbation to the chain of pendulums when you start them all in the up position, they will start to fall as in this video with a real well-defined velocity. When you start to include or start to increase the non-reciprocal coupling, that now I wrote it in this form, that d minus alpha and d plus alpha, compared to the previous equation in which I wrote K1 and K2. In this way, I can alpha measures directly the non-reciprocity because when it's 0, we recover the usual situation. So when you start to increase alpha, you start to see that it controls the velocity of fronts, and even it can reverse it. So some funny things like all the pendulums starting to go in the up direction by themselves is something that can happen when you have non-reciprocal coupling, and it's a really unexpected behavior. So we analyze this indeed. So we try to understand how this will happen. So we try to compute the velocity of these fronts. Okay, so we employ what is called a linear criterion, and we also negate the Hopper dynamics of the front. And one can compute a velocity function that depends on a parameter k that the system determines by itself. And how is determined this parameter k? Well, you need to minimize the velocity curve against k. Okay, so for example, in the case of alpha equal to 0, the point in which you minimize this curve will correspond to the average velocity of this front. Okay, this nonlinear wave. As you start to increase the reciprocity parameter, you can see that the minimum starts to get close to 0, and so this means that it can the velocity can reverse its sign, meaning that you in this point is where it happens, the phenomenon I explained during the previous slide. If you increase even more, some weird things can happen to this velocity curve. For example, maybe there are no minima anymore. So we will see what happened in these cases. So we were able to construct a phase diagram based on how these fronts move in the system. Okay, so in region 1, we have the usual behavior. So fronts in stable state, pendulums in that position go to the down position. Then, if you increase the non-reciprocity, you go to region 2, in which happens the opposite. Pendulums tend to get up by themselves. Okay. For a special combination of the parameters, you go to region 3, in which it's really similar to region 2. The only thing that the only difference is that now the front has an oscillatory tail that leaves a pattern behind. Okay. Later, you have also region 5, in which this oscillatory tail and the front also reverse against velocity, and now this pattern will propagate over all the system. And this is a really unexpected thing to us, because in a system of one variable with only nearest neighbor couplings, this was not observed before. So this is what we call the non-reciprocity induced a pattern in the system. Okay, it was able to induce self-organization. Also, you have region 4, in which similar things happen. You have an oscillatory tail going to the left, okay, but you end up in an anomalous, the pattern is not able to propagate. Okay, so how we determine all these curves in the phase diagram? Okay, so that for that the velocity curve helps us a lot. So separating region 1 and 2, we have the condition that the velocity changes sign, so it's just 0 at that point. From 2 to 3, we ask for a point in which this number k that determines the stigma of the front becomes complex, and now it has oscillations. And similarly, from 3 to 5, again, a convective instability occurs, meaning that the front reverses the velocity, the sign of the velocity, and but not this time with a complex also k number. And these two curves are special because they cannot be determined easily with the velocity, so I will explain them later. So here I show some of the dynamics in these other two regions that are kind of unexpected. I already explained to you regions 1 and 2, and here there are some videos of region 3, 4, and 5, where I put emphasis only in region 5 because it's the most interesting to us, because it's the self-organization that emerged due to the non-reciprocal coupling. Okay. Here you can see how after a long transient, then this pattern starts to propagate throughout the system and is sustained permanently in time. Okay, as you can see here in this small animation that I made. Here you can see the periodicity of the pendulums in the down position. Okay, it is worth to mention that these three regions, 3, 4, and 5, only appear thanks to the non-reciprocity, but also thanks to the discreteness of the dynamical system. Because when you try to construct the continuum limit of this equation, you only will recover regions 1 and 2. So regions 3, 4, and 5, the 5 that we are most interested in, are a consequence both of non-reciprocity, but also the discreteness of the system. Now I will explain these two other curves that were not easily explained by the velocity curve. So first, what I call the variational limit. I call it this way because the dynamical system has a structure in which it can be written as a it can be derived from a functional, okay, a free energy that is usually called that has this shape. And when you compute the temporal derivative of this functional, this free energy, it will decrease only if this d is greater than the alpha parameter. Okay, so whenever d is equal to alpha, we cross this variational limit, and then we don't know what happens with this free energy. Maybe it increases or decreases, we don't know. We are only sure that it decreases only when this condition follows. So if this parameter d corresponding to the reciprocal coupling part is lesser than the non-reciprocal coupling part, then we expect permanent dynamics as we observe with the permanent pattern that emerges. Then later I will explain how this pattern emerges. So this was also not captured by the velocity function. So the origin of these periodic solutions, both in space and time, this pattern that is permanently traveling, as I showed you before, has an origin due to the saddle node on invariant curvification, that is abbreviated ST. Okay? So here are the equations that I derived for this curve based on a simple theory using two pendulums. And what happens is that, for example, here I show the phase space when using only two pendulums, okay? And you can see here are the node lines, and we see at least 5 equilibrium points. 2 of them are hyperbolic, okay? So these hyperbolic points are the crucial part of this because the unstable manifold of them is what creates the invariant curve. And this invariant curve survives after the annihilation of them by a saddle node. So 2 saddle nodes occur at the same time. And here I show you a trajectory of the permanent limit cycle after the bifurcation. So this limit cycle is what creates the pattern, okay, that we observed before. We also study some of the noise effects of this data, how the noise will affect these dynamical properties. And here is a phase diagram now of the steady state. So we analyze the infinite time of these simulations. And more or less, region 1 is the same as before. We will go a homogeneous solution. And the curves that we previously derived, in particular, the curves varied in region 1 and 2, and region 2 and 3. Now, I changed a little bit the nomenclature, okay, are something similar to what happened without noise. So, and the noise is a small perturbation in the case of 1, 2, but a big perturbation in the case of in regions 2 and 3. What is most important of this is that the pattern that emerged before, that now is denoted with the region 4, is robust against the noise. So, and this is thanks to the snake bifurcation and the limit cycle that I explained you before, because limit cycles are robust against noise also. So later, we decide to analyze what happens if we vary the boundary condition that I explained you before, because we were forcing an initial pendulum to be always in the up position perfectly. So this, we know that this cannot happen in reality, so we let this boundary condition to be some other value x, and it will be small because it will help us to calculate, okay? So what happens is that boundary layers will emerge, and they will be able to be really big, okay? So here I show the equilibrium configurations for different values of the non-reciprocity parameter, okay? And in the case in which this alpha parameter, the non-reciprocal parameter, is small, we observe what I call small boundary layers because they are formed by a few pendulums only. However, when you cross a critical value that corresponds with the convection stability, you observe that a lot of pendulums are part of the boundary layer. Okay, this is the equilibrium position. And how you end up in this configuration? Here I show an spatio-temporal diagram. So you start, for instance, with something that is similar to a front or to this kind of solution that has this nonlinear way. And you see an apparent motion of a front, but suddenly stops, and then the equilibrium is achieved. And you define what is called the number of pendulums that form the layer, NC. Okay, so to understand how this NC emerges and to try to compute how much it varies, we decide to analyze the equation of motion in equilibrium. So we put the temporal derivative equal to 0, and what we have now is a nonlinear map, okay? Because we have the theta sub I plus 1 as a function of theta sub I and theta sub I minus 1. So it depends on the variables. However, the case of d equal to alpha is really enlightening because it transforms this equation into a one-dimensional map. You see, if d is equal to alpha, this term vanishes, and you are left with a one-dimensional map that I showed here. Okay, so the important thing of this map is that we are connecting, or somewhat connecting, because we start with an epsilon value, to fixed points. Okay, and we know that fixed points are reached by the dynamical system only after an infinite number of iterations. Okay, so I had the idea to only analyze the initial part of this map iteration, because at this close to the fixed point, as you can see here, is where most of the steps will occur. After doing this, I was able to derive this formula for the NC value that determines the size of the boundary layers. This is a formula, okay? And here I show, for example, in the case of alpha greater than alpha critical, in the case where the giant boundary layers emerge, we have perfect agreement between the theory and the numerics. And in the case in which alpha is lesser than this critical value, we observed that the NC value is dominated by the D parameter, and alpha plays no big role, okay? So in this way, we characterize these boundary layers that emerge as a consequence of perturbing the boundary condition that we initially used. All these observations and works motivated me and my lab mates to try to create an experimental setup. So this was done in collaboration with Pedro Aguilera, Amaro Moya, and Manuel Diaz. Some of them are here right now, that were able to create a stable cell in an optical experiment. And one can observe that the propagation of one state over the other can be controlled, okay? So in the first video, I showed you that the perturbation propagates both ways. However, when you make some modifications, in particular, we use translated optical feedback. You can control if the propagation goes to the left or to the right. So this could be explained with a model with non-reciprocal coupling. Okay, so these are the measures of this propagation velocity, and then I try to compute if we could reproduce these curves. Okay, so I was able to analytically predict the linear zone of this diagram with this complex formula that I derived using this equation. Okay, here I show how the plane true for the velocity of these fronts now into the stable state, because they connect two stable situations now. a little bit different. So you use a little bit different techniques. In the right graph, I show the perfect agreement between the formula derived and the plain true of numerical simulation. Okay. So this is really nice and it's work that we are developing. So now I will jump to the other part of my talk, in which I will talk about the non-reciprocal coupling, but now in population dynamics. Okay. So what is the context? The context is that plants are known to affect each other when they are in a community. Okay. And typically, when scientists try to model this mathematically, one uses kernels of interaction, okay, which could display a reciprocal and non-reciprocal interaction between the plants. Okay, so a little bit of explanation of how we do this. We start with the most basic equation for population dynamics. That is, how the population will change. It changes according to the births, the deaths, and also the migration that happens. Okay. In the case of plants, obviously they don't move because they are fixed in the land, but other agents, external agents, can propagate the biomass via seeds or other mechanisms. Okay. So what is important to me is that you can have several mathematical models of this. For instance, you have families of reaction diffusion models that couple this biomass with other relevant variables such as water. And also you have interaction distribution models that only takes into account the biomass and all the other agents are hidden in the interaction kernels. Okay. What is important is that these models predict similar self-organized states as the environmental conditions change. So just to pick one, and we start to analyze the interaction distribution models. And we try to explain how non-reciprocity can emerge in these systems, okay? So the kernel is what dictates how one individual is affected by the other. So it's the continuous analogous to this matrix that I showed you in the very first slides, in the strings and masses slide. And we will assume that the kernel will have the same symmetries as the system that we are modeling. Okay. So, for example, in fog-dependent ecosystem, or when there is a slopes, we have two symmetries that are broken. First, the rotational symmetry, and also the space reflection symmetry in the direction of the slope or the fog, for example. Okay, and this property will render the kernels non-reciprocal. So if you interchange the two positions of the plants, they have a different value. So we proposed a kernel that has these simple properties that correspond just to a Gaussian kernel that is shifted. Okay, so here I show some examples of how this looks. So the orange curve corresponds to when you put this parameter alpha 0 that will measure the non-reciprocity. Here I show a picture of the fog-dependent ecosystem that I am most interested in. That is in the north of Chile. That is composed of a plant named Tillandsia lambeki. And what we find really interesting of this plant is that the properties I mentioned before, that here is evident that non-reciprocity will emerge, but also we notice that the boundaries of these patches of vegetation are really marked. So we could play with the boundary conditions more freely. For example, in the literature, one usually finds that scientists use what we call periodic boundary conditions because they have a mathematical simplicity for the numerical simulations. However, we will fix, for instance, in one of the boundaries that the biomass will go to 0, as we observe in these pictures. The consequence of these two ingredients is that a pattern will emerge thanks to the non-reciprocity, because it will favor one direction, of course. But also, as a consequence of the boundary, we see that the system is permanently disordered, because in the border there are weird things happening all the time, and it creates this like forks that you see here. So we studied more in deep this also, but previous to that, I also wanted to propose a more simple and even simpler equation to try to describe this. So we pick up this interaction redistribution model, and close to all these conditions that are explained in this reference, I was able to derive this equation that I baptized for this occasion, the equation for vegetation biomass in extreme asymmetric condition or extreme anisotropic conditions. So what is important here is the last term that has partial derivatives only in the x direction, and they are a consequence of this high asymmetry that is happening in the system. All these parameters are function of the kernels, of course. Okay, so what happens is that in all of these three models, the interaction redistribution, the reduced model that I derived, and also reaction diffusion model that I picked from the literature, we observed that when we start to increase the non-reciprocity, that also we call it here the advection transport of other variables, there is a relation between these two terms. We observe that you can transit from a regime of perfect stripes, as shown in left, to a regime in which the stripes are really distorted and have a lot of these defects, these forks that I show you here more big in the right. Okay. So we started to analyze these defects because they could be recognized in what is called the amplitude field of the pattern. In the amplitude field of the pattern, these defects looks like holes in there. And the reason is because they are phase singularities of the complex function that describes these waves. When you compute the number of these defects versus the direction that loses the symmetry, this is the x direction, and you plot it in the downstream direction also, so here x is increasing downstream, you observe that these effects are not random. They follow a well-defined law, okay, a curve. So we try to explain what is the origin of this curve. Okay, so what happens is that the distribution of these defects that are called dislocations can be understood thanks to the amplitude equation. Okay, and what are the amplitude equations? As I told you, the amplitude is what describes this wave that emerges in the system, the pattern itself that is traveling. So in all these models, there is something happening that is a wave instability. So when you cross a critical parameter, the pattern emerges, and you can compute what is called the amplitude equation. In this case, you will end up with an equation that is called the complex Ginzburg-Lagrange equation, and it will have an advective term because these patterns are traveling. Okay, these parameters are usually complex. And the most important thing is that in the regimes that we are studying, the scientists previously analyzed how these defects interact and how their number evolves in time. Of course, in the case where this transport is equal to 0. So they have this coarsening law in which the number of defects will decrease with time. And here I show you some animations of this. So This is what's happening in the numerical simulation that I showed you before. You have a lot of these defects emerging from the boundary, okay? But if we follow them, a box with the group velocity, you will see that they are interacting and they are annihilating. Okay, this is what creates this coefficient law. So, as the boundary is permanently emitting these effects, we can interchange the role of time and space because the boundary permanently sustains the creation of effects, and then downstream they are interacting, making this in the solitary reference frame. To be able to produce this in the amplitude equations, we have to consider the boundary conditions that I mentioned before, because the boundary conditions will render some of these parameters inhomogeneous, and they will help to nucleate these defects deterministically. Okay, these are not nucleated by random perturbations. And this is what allows us to explain this curve that, and we try to fit this law, and it goes really well. So then we try to see if this could be observed in nature. So we analyzed 3 different patterns that more or less had the conditions of our theory. So we have the pattern in Chile made of tilapia and baby, and also some other patterns in Sudan and also in the USA. Here I show the pre-processed images that I used to make the analysis. Once you define the region of interest, the region where the pattern is existing, we needed to define a direction, an x direction, the direction where the symmetry is broken. And for that, we use satellite data of the topography of the system. So we computed the direction of greatest flow, okay? And so we use the slope as a source of this reciprocity. We see that more or less in all this system, the slope, the degree, the angle of the slope is more or less homogeneous. So it goes well with our theory. And once this direction is defined, with a skeleton algorithm, and one is able to compute these forks, okay? These points in which the right divide and where the points in which they end. That corresponds to this location in the regional system. We had to do this because these patterns are really noisy and we will not compute an amplitude field. Doing that, we were able to see that in this direction, indeed, the defects are decaying. Okay, so the permanent dynamics of the model that the models predict leave an imprint in the actual systems, okay, that one is able to observe. Okay. And to all of them, we try to fit our law, and it works more or less pretty well. Lastly, I want to talk about the importance of this law, or how this law could be important to us, and it's because the pattern suffers bifurcations as one ecological relevant parameter is changed. For example, here I plot the bifurcation diagram of how the biomass evolves when you change a parameter that is called eta that measures the mortality of the plants. So if the mortality starts increasing, we expect that the ecosystem collapses and everything dies. So what is interesting is that the ecosystems that are displaying the law of decaying dislocations correspond to the branch of yellow points. So they are the last branch of stable patterns, okay? Compared, for example, to the branch of perfect patterns, denoted by red points, or a branch of really complex patterns denoted by the blue points that contains a constant number of defects across all space. So this tries to say that studying the dislocations and also including the non-reciprocity in the models of population dynamics could be really important to try to understand these systems because it says things about that are ecologically relevant. So now I will end up with the conclusions and perspective. First of the frontier control of a chain. We expect to continue in our experimental efforts after having established all the law of motion of this linear wave, both from into the unstable state and from into the stable state. And we want to contrast the more scenarios with the reality, okay? Also, generalizations to this time non-linear, non-reciprocal coupling, because this talk, in this part of the talk, I only speak about linear non-reciprocal coupling. This, when you put them to be non-linear, it would explain the out of the linear zone of these curves that are experimentally measured. So it's a direction in which we want to move on. On the other hand, in the case of the non-reciprocity in population dynamics, having established the qualitative behavior of these patterns, my intention now is to be more quantitative. So to be able to make actual predictions based on actual parameters. Okay, so for this, the individual dynamics of plants could provide insights that are really important. And this is what I plan to do in my future work, okay? As a last comment, I want to mention that in this presentation, I addressed 3 of the works that are present on my dissertation in the actual manuscript. You can find online. However, also you can find these other 3 works in the same manuscript online that you can read. However, due to the limited time of the presentation, I could not explain everything. So thanks all of you for your attention.
Okay. We'll continue with now the question of the commission. So as a tradition, so we will start with, we have 2 criteria, the distance and also the parity. So in that case, it's difficult, but I assume that the more far is a hood, but Karin is a woman. So we will start with Karin and after that with a hood. Okay, Karin, you can start. Karin from the University of Rey Juan Carlos from Spain. Okay, Karin.
Thank you, David, for your presentation. I have a few questions more than maybe we can start with the first work.
Okay.
So why you I don't know if you already mentioned, I didn't I don't remember, but how you measure the mean speed, or what do you consider to measure the mean speed of the front, and why you measure the mean speed and not the vector?
Okay. Thanks for the question. So to answer the first one, first one needs to define a position for this front. So we created a criteria for this position. Okay, and the criteria is just, for instance, you fix a value. For instance, for example, it can be the middle value between the 2 equilibria that you are connecting, and once the points cross this value, you define a position, and then you will have a position versus time, and you compute the derivative and you average it. And to answer your second question, why not to compute the whole velocity, how it depends in all the parameters? Because mainly what the velocity does is it makes a small oscillation that it can be neglected for our efforts. So I have a small graph showing this small oscillation, and we can see that it is really small, so we neglected it and we don't. But you could make more effort to try to compute how this oscillation behaves. Yes.
Okay, thank you. And related to the second part of your presentation, I was wondering if, okay, we know that due to the boundary condition that you put to the simulation, then you create these defects. But is it possible? Have you seen if you perturb in the middle of the simulation, will you have those defects or no?
Yes, indeed. Indeed, that is what happens. You can perturb the system at any point, and then this disordered pattern will propagate to all the system.
Yeah. But before that, I know that after a few simulation iterations, your initial condition will go through all the system. But if you have an initial, you put an initial condition, you perturb in the middle without taking into account the waves that were created by the boundary. This initial condition will have defects?
Yes, it will have defect because it's something that is happening. It's like a local instability that happens when you are connecting to equilibrium. So you will have defects when you perturb in the middle, and in this transient, before these waves are propagated to the boundaries, you will see the effects interacting also. Yes, but this transient is really short because
I know you have this wave propagation. Okay, it's okay for me.
Thank you.
Thank you.
So now we continue with Professor Ehud Meron from the University of Ben Gurion. Ehud.
Ehud, we cannot hear you.
You're on mute.
I muted myself.
Now it's okay.
Now
Thank
it's
you.
okay.
Thank you for the nice presentation. I actually asked you many questions a week ago, so I want to repeat them. And let me ask you a more general question. You presented, or your thesis consists of studies of some quite simple systems physically, like the Sprengel-Konturova model that can model a few mechanical systems and so on, which are, I'm not saying the problem is simple, but the phenomena are relatively simple in their complexity. And on the other hand, you also deal with a living system, like vegetation patterns. And this is a far more complicated system. And one of the complications is that living systems in general consist of several levels of organization. In ecology is usually the individual plant, the population of many plants of the same species, different populations of different species that constitute a community, the ecosystem level, and so on. And if we are thinking of climate change and the phenomena that on the regional scale that are related to it, like droughts and desertification, then how would you view vegetation pattern formation in that regard. Is this a mechanism to cope with water stress? And if it is other additional mechanisms working at different levels of organization, for example, at the level of a single plant to cope with water stress, or at the level of a community of plants? Do you expect interactions between mechanisms operating at different levels of organization? All these are hard questions, but still I would like to have your kind of view about them.
Yes, thanks for the comment. Indeed, you can start to make more complex systems because life is complex. So to make accurate predictions, we need to consider all that is happening, all the time scales and all the space scales. And it's true that in ecosystems, there are many agents that are playing a role. So I agree with you that the natural next step of all these works is to see if we can reproduce this in even more complex system and to test to what extent these universal behaviors happen. But I will expect that in, for instance, in vegetation pattern formation, the bifurcations that I showed you about patterns to happen, even if you consider many species and other agents, because they are related to the bifurcations that happen at the level of the amplitude of the pattern. So I will expect them to be rather general, but how do you reach these amplitude equations will be a really hard problem to solve. I agree. I don't know if that more or less.
Okay. Answer to some extent. Thank you.
It's okay, Hood?
Yeah, I'm fine. Yeah.
Okay. So now we continue with the Professor Ricardo Martinez Garcia from the Helfand Center in Germany. Ricardo?
Thank you very much for the presentation, David. Yeah, I also made you a lot of questions in the private defense and also a few months ago, so it's getting harder and harder to find questions for you about your work. But I was very interested in this experimental setup that you showed to measure biostability in cells. And I was wondering, how do you adapt this model of oscillators to one single cell? What is theta of I within the cell? Is some region of the cell, or how is that?
Thanks for the question. So to explain a little bit more, what my lab mates measure is a light intensity that is reaching a camera, okay? So this stability is between two intensities of light.
And theta of I would be intensity in a region of the cell.
Exactly.
Okay.
This theta parameter that I used to model after will correspond to this intensity in this case. And this function B will describe a stable potential.
Okay, very, very interesting. And one final question about the vegetation part that I missed all the times we discussed that word before. So you analyze the number of effects on different regions, and then counted the number of effects as a function of the distance to some origin, no? Exactly. Do you have temporal data for those systems, so you only have one snapshot from today? So have you see if you are able to get patterns from, let's say, I don't know, 10, 20, 30 years ago?
That's a really interesting question, because we initially tried to see if we could observe the dynamics of these defects in temporal scale. However, all the photographs that were like freely available by satellite were not good enough to discern this. So we could not observe temporal data. However, a way to justify how to use one single snapshot is that if you make the patch big enough, you can expect the spatial ensemble to be equivalent to the temporal ensemble. So it would be really nice to observe the temporal dynamics, but for the moment, we are not able to.
Okay, well, that was all the small questions I had remaining. Thank you again for the presentation.
Thank you.
Thank you, Ricardo. Now we continue with Professor Mustafa Tlidi from the University of Brussels. Mustafa.
Thank you, Mr. Chairman. Thank you very much for this wonderful presentation. Actually, I can see your thesis as a function of three theses. One related to non-basic quantum coupling of kind of oscillators, liquid crystal cells, and a non-collective population dynamics. And in each of these areas, published in important papers in high impact international journals. In the third part of the area, which is a top journal for physicists, for the discussion part, as we published in this prestigious journal about science advances, and also for the part related to liquid crystals and Marcel lab. When we start to write thesis, I was wondering how we can find a common denominator for an umbrella with which we can make the manuscript coherent or self-coherent. When I received the manuscript, I was really impressed by this non-reciprocal which made this umbrella. Structure rather coherent. I got to know you when you visit us in Brussels.
When?
No.
Actually, students, I'd like to mention here Camila Castillo Pinto, Sebastian Echeverria, and you. We were only through this project, in cooperative project between Belgium and Chile, and it was something like 18 projects. We were ranked #1 because of the only project that had this exchange that was planned. We realized all the objectives of the project. For that reason, we were ranked, and immediately the project was renewed for the next 3 years. And I would like to mention, as I said, I don't have any question to ask because we already discussed in depth your thesis during the private conference. I would like to mention maybe some stuff. Yeah. So also this, which I will call the Pinto law, logarithmic x divided by x, is a very rather obvious law, because we didn't mention that in the Marcel using liquid crystals, Pedro was able to reproduce this law in a very precise way. Why? Because all the parameters are controlled, and the experiment is the results are fiable from experimental point of view. Or in vegetation, it's still very difficult to parameterization of the model, essentially because the measurement of these kernels that describe the facilitation and competition are very difficult to measure. Measurement, you cannot distinguish between Gaussian or exponential or fluorescence for emissions. Where in optics we can measure this very precise.
Exactly.
Yeah. So also during your stay, I realized that you have a high level of culture and very friendly, and also scientifically, I think you are one of the best student, PhD students that during this career. Finally, I would like to mention the statement that you citation to Poincaré that you make in the first part, just because just after before the or after
The summary.
yes. And this statement is very deep because it reflects somehow in it says that the scientist does not study nature because it is useful. Scientist studies it because he delights on it. And he relied on it because it is beautiful. Thank you very much.
Okay, now it's my turn. So I changed from chairman to now to the advisor. So my name is Marcel Ter, I'm professor at the University of Chile. So I was advised to David. So first of all, I'd like to congratulate to David. David is an exceptional student and brilliant disciple, I prefer to say. So I formed several students for maybe 2 decades, and maybe David is one of the best students that I really have. So I'm really proud for you. And I'm happy in some sense because you finish your thesis, but a little sad because you left me, and a student like you is not easy to find, to be honest. So in that sense, I'm really happy for you, and maybe sad for me, but it's the life. So, but I say every time, so I expect that a lot of things from you as a discipline. So only maybe mention a small history, and after that my question. So the small history is when, for instance, David visited to Mustafa. So Mustafa proposed to him to study this kernel, but we have real data, but apparently the data is not enough to characterize the kernel. But David in this visit of 3 or 4 months, if I well remember, anyway, found a way to take the data and discover another problem. So even calculate the thing, and we move completely in another direction, completely directed by David in that sense. So this reflects your quality. So I'm really happy for that. So my only criticism for the moment, you are very good theoretician, but not very good experimentalist, but it's quite good. It's not bad. And okay, my only question is, you have a lot of results. So your results. So my question is, in your opinion, which is the more important of your result and why?
Which is the most important? Wow, that's a really difficult question. Well, from my perspective, and because it's what I like the most, I would say that the work related to vegetation patterns, because it's what initially delighted me and convinced me to follow this path. And it's what I intend to follow in my career.
Okay, so now if some doctor have any question to ask, there is no doctor, so there is no question for this part. So I propose to the public to leave, but not to wait deliberate, and after you can enter to, the last deliberation.
I also leave.
Yeah, you must leave. You cannot deliberation. Okay, Mustafa, maybe you put there and you put here. Okay, so there is some formality that I must to send you when we finish maybe today. We send soon as a letter for each one, because normally we have this is the official document, but for this official document there is your name, But in the document that I will send you, our dean have the right to sign for you. Okay, you sign this document, and after it's in Spanish. Sorry for that, but this is the legality on Chile. And after that, our dean will be signed for you. This is the official legality. I cannot send you and sign by internet because this is illegal in the Chilean legislation. So I cannot send you this, but I can send you the equivalent. So first, I will send you everyone. So the only can sign is Mustafa because he's present. Okay, first. Okay, so now we must deliberate about the qualification of the thesis of David. I assume everyone. Well, first, I don't know if one like to ask another thing, but I think more or less we agree. But I don't know if one like to say something, but really I say honestly, David is an excellent scientist. I expect a lot of him. And well, we will see what happens in the future, but really I expect a lot of him. So I expect become professor, I expect in Chile or another place, and also expect become the legacy of our university. I mean, we have a long history, maybe start with Enrique Terapegui, but we have several students of Enrique and the student of Enrique and so on. We have this nonlinear science in Chile, which is one of the bigger branches in our country anyway. So David, I expect continue with this legacy. I expect, this is my opinion, but I don't know if one has to say any comment that have, I don't know. I don't know, Mustafa, you like to say something maybe? No, you can.
Well, I'm not that familiar with David as you are, but
sorry, it's one moment. It's just that, Marcel, you are sharing the screen to YouTube.
Oh, sorry, guys. Say me yes. This is bad. Okay, maybe. Okay, wait, oh yeah. Oh, I forget this answer. Sorry.